Let us continue from where we had stopped yesterday, right? So what were we doing, by the way? The DTFT, right? So what is DTFT? Hmm. So yeah, we have the formula here, right? That of DTFT, very similar to your Z transform. You keep telling all the time the thing, okay? And there are some standard questions. X of n equal to alpha to the power n into u of n, whose answer also looks very similar to that of your Z transform. Z replaced by e to the power j omega. But there Z transform existed for both alpha greater than 1 and alpha less than 1. For both the cases, Z transform would exist. Okay, for both stable region and some of the region would be stable, some would be unstable. Whereas here, now that we are in DTFT, DTFT exists only for the stable region. It does not exist for the unstable region. And also, I want you all to remember the shapes, right? So this is called as an exponential. Okay, alpha to the power n into u of n is a complex exponential whose shape, the DTFT of a complex exponential, is going to be a bell shape like this. Okay, it's going to be a bell shape. See, actually, you are supposed to draw from minus pi to pi only. The textbook fellows, they draw it. It's difficult for us. It's going to be bell shape. What you can do is you can substitute for omega equal to 0 in the expression to get the value, to get the value at the midpoint. Then you can remember the expression. This will be the expression for the complex exponential. Okay, so you can substitute, draw something similar and write the answer. That's how it works. Okay, nobody expects you to actually substitute the values from minus pi to pi and draw this kind of thing. Okay, then yeah, this was a complex exponential. Then the next thing we saw was that of a rectangular pulse. Okay, everything discrete. Okay, everything discrete. This was a rectangular pulse which exists from minus m to plus m. Okay, something what I've drawn from minus 3 to plus 3 maybe. Okay, and the answer turns out to be, and it answer turned out to be something like this. Answer turns out to be something like this. Okay, so it's a rectangular pulse because see, the envelope of this is rectangular, right? That is why we call it as a rectangular pulse. For any m, the answer will be sine omega by 2 into 2m plus 1 divided by sine omega by 2. Suppose I have values my rectangular pulse starting from something like minus 4. Say it starts from minus 4 and ends till goes till plus 4. Okay, then my answer would be sine omega by 2 into 2 into 4 plus 1. Okay, 2 into 4 plus 1, 8. Omega into 4.5 divided by omega by 2. Okay, so this is a standard result. Okay, this thing here is a standard result. Okay, for a rectangular pulse, which you are supposed to remember. Even the alpha to the power n into of n, that also is a standard result which you are supposed to remember. Okay, so what other problem we saw? Yeah, then the other thing we saw, the shape of it. The DTFT of a rectangular pulse is something like this. See this particular shape. It is called as a sink. A sink means something, a bell shape whose amplitude goes on reducing on either side. The thing is symmetrical on either side. The values on the right and the values on the left, you can see it is symmetrical from the y-axis. Okay, and from minus pi to pi. This is what we are supposed to draw. Remember, sine divided by sine, or sine divided by something that is growing on either sides. Okay, that gives you these kind of shapes, the singles. And then we saw a dual of this, right? So the DTFT of a rectangular pulse was a sink, and then we saw the next problem that we saw was DTFT of a sink pulse. So this example, what we did was, here we took example of DTFT of IDTFT of a rectangular pulse we saw, and that turns out to be a sink in the time domain. So it was like a duality, right? Rectangular in time domain is a sink in frequency. Sink in time domain is a rectangular thing in frequency. Okay, so remember this. Okay, so this is also a standard result. So if possible, we will Remember this. Otherwise, anyway, all problems can be solved. But remembering standard results makes it little easier. Okay, it always makes us, solving problems little easier. Okay. So now what is now? Let us continue. These all things what we did yesterday. Now let us continue. Okay. So what was it? Yeah, one more standard result. So this is the most usual suspect, delta n impulse. So DTFT of a delta n, as you saw yesterday, how what do we substitute here? By the way, x to the power j omega. There is the formula, but since delta n exists only at 0, then the whole summation does not come into picture at all, right? The summation simply vanishes. So we will only have 1 into e to the power 0. That will be 1 for all the values. So DTFT of an impulse turns out to be a constant value in frequency domain, actually from minus pi to pi, since the same pattern repeats. Okay. On the contrary, if at all you have an impulse in the frequency domain, okay, on the contrary, if at all you have an impulse in the frequency domain, how do we solve this, by the way? So here the question is, find IDTFT of a impulse. Find IDT of a impulse. So this is the standard formula of IDTFT, 1 by 2 pi minus pi to pi delta omega into e to the power j omega. Delta omega is our signal, x of n, x to the power j omega, right? Now here you can see what will be the value. Author says the value is 1 by 2 pi. Do you agree with this? Author says value is 1 by. Now see, here there is an integration fine, right, from minus pi to pi. Okay. uh, there is an integration we should do from minus pi to pi, but since from minus pi to minus 0 and plus 0 to pi, there is nothing, right? It's only 0. That is why the whole integration does not come into picture at all, right? The whole integration does not come into picture at all, and we need not take this integration into consideration. That leaves us with x of n with only 1 by 2 pi into 1. Okay, 1 by 2 pi into 1. Okay, do not get confused. So this entire term is now gone because impulse does not contain any value, so there is no integration from minus pi to pi, rather it is only 1 by 2 pi. Okay, so we saw here DTFT of impulse is constant, and IDTFT of an impulse is also a constant. Okay. What this thing, of course there is a scaling factor, of course there is a scaling factor. This is also something similar to the dual. Okay, a constant in frequency domain results in a impulse in the time domain. Impulse in the frequency domain result in a constant in the time domain, right? Now you can see here, let us try to make some sense out of this. You can see this x of n, right? If at all I join the envelopes, you can see this is like 1 by 2 pi, 1 by 2 pi. It's a constant voltage. Remember, you simply turn on the light and you can see this is just a constant voltage. What this constant voltage indicates, what is the frequency of this? The frequency of this is 0. So we keep telling that the DTFT is the frequency domain representation. Now since this impulse is occurring at 0, okay, this is what it indicates. That means a signal which is having a 0 frequency or a DC, you can see, is having uh, impulse, right? That means it is having, so this frequency domain representation, it is representing that there are no other frequency components from minus pi to pi, but only at 0, which is DC. Okay, remember the standard result, right? Remember this standard result. Okay. Now we'll continue. What other problems you can get? Okay, yeah, here is a problem. What is it? Find DTFT. Alpha to the power n into u of n minus 4 they have. So what we'll do for u of n minus 4, what we can do? Yeah, we'll start with the formula. See, 4 to infinity. Okay. So instead of say this u of n minus 4, right, it starts from plus 4 and goes till infinity. That is what we'll do. We'll change the limits. We'll change the limits so that this starts from, instead of 4, this starts from 0. So here we will have n, say something like put k is equal to m minus 4. So here n plus 4, okay, right? So we'll get n plus 4. So this entire thing, 3 by 4 e to the power j omega to the power 4 will come in numerator. Other than that, you will be left with only this particular term from 0 to infinity. So which is this particular term multiplied by 1 divided by, right? 1 divided by alpha to 1 divided by 1 minus alpha. 1 divided by 1 minus 3 by 4 into e to the power minus j omega. Okay, got the thing, got the thing. Or we can solve it using properties also, right? So I could have written the same question as 3 by 4 3 by 4 whole to the power minus 4. Shall I? 3 by 4 to the power 4 into 3 by 4 to the power n minus 4. 3 by 4 to the power n minus 4 into u of n minus 4. I can do this. I can do this way also. Then this is a constant anyway. 3 by 4 to the power 4 is anyway a constant. Then what I will do, I can apply some property, okay? The time shift property which I applied in my DTFT Z transform. Same thing I can do here. Anyway, here it was not necessary. We have done the direct substitution and we got the answer here. So as expected, the alpha to the power n t of n we have shown. Here also it's a bell shaped curve. Here also it's a bell shaped curve. So as I told you, so these things are better done by you on a scribbling pad rather than me teaching you. Okay, yeah. So what other questions? Okay, okay. Here is one more. Alpha to the power magnitude n. DTFT exists? Yes, it exists. Okay, for magnitude alpha less than 1. So this we know, right? Alpha to the power n. What this means is decaying exponential. It's a tenth. Decaying exponential. It's a tenth. So what this means? So this is alpha to the a to the power, right? A to the power n, and on this side a to the power minus n. Okay. So the substitution has been made here. You can see for negative part. Okay. For positive part, it is a to the power n. For a negative part, it is a to the power minus n, right? And then afterward, the substitution has been made, and you have got a value here. Okay, and you have got a value here. Yes, of course, the steps are missing here. You have to change the limits, and then these things will come in denominator and so and so, and then finally you get your answer. Okay, so this one here is a very 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 important question. Okay, this is a very important and a trick question also. Important and trick question. Okay, alpha e to the power minus j omega whole to the power n. Yes, on the right side it is alpha to the power n. On the left side it is alpha to the power minus n. See, you can see this minus has been taken outside. Okay, I hope you are not getting confused. And then you have the shape of it. So as I told you, a very important question. Okay, now one more question, straightforward. Here they have given you the value of x of n. So what you have to do? We know x e to the power j omega. What is the value of x e to the power j omega? You just have to substitute. So x e to the power j omega, x of n e to the power minus j omega. X of n e to the power minus j omega. You simply have to substitute and get the value here. Okay, you just have to substitute and get the value here. By the way, one thing, what is this 1 by 2 doing here? I am not convinced with this 1 by 2. This is fine. What is the expression for x of omega? I took this thing from Heikin. I'm not convinced with this. Let us see. What is the Fourier transform? What is the expression for Fourier transform? Yeah, here is the expression for Fourier transform, right? X to the power j omega equal to x of n e to the power minus j omega, right? Okay, so this is a straightforward question. So here what you have to do is, so let me tell you, x of n e to the power minus j omega n. This thing is not there. Okay, sorry. This 1 by 2 is not there at all. See, everything, all magnitudes are 1 only. Now you have to substitute at omega equal to this one here exists for e to the power j omega 4 at 2, right? The entire thing exists here. I think, wait a second, wait a second, wait a second. Let me skip this. Let me just skip this one problem. Okay, I will come to this tomorrow. This is an answer for a different question. This is answer for a different question. Okay. Okay. Hmm. Now here is a question. Here is a question. X of n equal to minus alpha to the power n u of minus n minus 1. We remember this thing, right? This question is a usual suspect. So in Z transform, alpha to the power n into u of n, alpha to the power n into u of n, and minus alpha to the power n u of minus n minus 1, both of them had a Z transform 1 divided by 1 minus alpha or a z to the power minus 1, right? Remember this. Remember this. Now the question is a to the power n into of n. How can, but here what is said that if at all this is given, if at all the signal is right sided, if at all the ROC magnitude z is greater than a, then we will conclude that this is right sided. And if magnitude z was less than a, if magnitude z was less than a, we will consider it as left sided. But now this is DTFT. Now this is DTFT, right? The discrete time Fourier transform. So what here we have to do is we just have to solve straight away, like Z transform, Z replaced by e to the power j omega, right? So Z transform of minus a to the power n u of minus 1 is false. 1 divided 1 is z to the power minus 1. We'll simply replace z by e to the power j omega and we'll get this answer. Fine. Then what's going to happen is the difference is, see, earlier a to the power n into u of n also you got the same answer, minus a to the power n u of minus n minus 1 there also you got in the same answer. There is no ROC here, but the difference is alpha to the power n into u of n will have DTFT only if magnitude a is less than 1, for which less than 1, for which the right sided sequence was converging. Here this thing exists for the DTFT, here also exists. This is right answer only for magnitude a greater than 1. What's going to happen if magnitude a is greater than 1? If magnitude a is greater than 1, the left sided sequence is going to be a decaying exponential. Okay, so you can see both the signals a to the power n into u of n minus a to the power n u of minus 1 minus and minus 1, both of them have the same DTFT, but a to the power n of n exists only for magnitude a less than 1, and this here exists only for magnitude a greater than 1. Okay. Okay, this is also important and sort of a trick question. Okay. Remember this. Okay, now what next? Now what next? Okay, now there are properties of Fourier transform. Now see here, everybody. So what you have to do is on your notebook, I hope everybody is having a Ganesh Rao or the solution manual of hiking, or yesterday I have uploaded that signals and system Sham series. Okay. I have uploaded it, just go through it. Okay, just go through it. There also neatly all the proofs have been given for all the properties of Z transform, the discrete time Fourier transform and continuous time Fourier transform. They are there for syllabus, and in every question paper at least two properties, one from either Z transform or from DTFT, will be definitely asked. Okay, now since it was a theoretical thing, I did not cover it. Okay, because it was there in the textbook, you can go through it. I simply did the statement, but I want you people to be comfortable with those statement and the proof. Okay, even in the test whatever I conduct, I won't ask it, but in exam definitely that question is going to come. Okay, so here is one assignment which when you report to me in the college later, you have to submit to me all the proofs. Okay, proofs of all the properties. It will be a rehearsal for you for the exams also. Okay, now for the timing here I will not cover the proofs, I will simply run through the properties, because using those properties we can cleverly solve the numericals. Okay. Using those properties we can cleverly solve the numericals. Let us see what all are those properties. Let us see which all are those properties. Yeah, here So which all properties do we have? Um okay, anything? Okay, so first thing we'll assume that x of n is x of omega, x1 of n is x1 of omega, x2 of n, the DTFT is x2 of omega. And assuming that the DTFT exists, okay, assuming that the DTFT, so what is it? Linearity. Periodicity. X of omega is periodic with period 2 pi. Okay, the first property is x of omega is periodic with period 2 pi. Okay, we have seen in all the problems that the same thing keeps on repeating. Then DTFT is also linear. A1 x1 of n plus a2 x of n gives you a1 x1 of omega plus a2 x of omega. That means an addition remains an addition constant. You can roam around freely about the transform domain. Time shifting. X of n minus n naught e to the power minus j omega n naught into x of, right. Here what was the z transform of x of n minus n naught? It was z to the power minus n naught, right. It was z to the power minus n naught into x of z. Remember, z to the power minus n naught into x of z. Similarly, here you have to simply replace z by e to the power j omega. Here you have to simply replace z by e to the power j omega. So this is one property, the time shift property. Another one is frequency shift property. A shift in the frequency domain. I think this property was not there in your z transform, right? The time shift property x of n minus n naught gives you e to the power minus j omega naught. Z replaced by e to the power. X of omega minus omega naught results in multiplication. A shift in the frequency domain results in a multiplication in time domain. And you can see the missing minus sign. You can see the missing minus sign here. See, minus sign here and a minus sign here. For omega minus omega naught, the minus sign here is missing. Okay, minus sign here is okay. So that was that. Conjugation. Okay, if at all x of n gives you x of omega, conjugation of x of n gives you conjugation of x of omega with every minus negative frequency converted into positive frequency, every positive frequency converted into negative frequency. Okay, we'll see it as and when some numericals arise, right? We will see this particular property. For the timing, for us, which are the important properties? Linearity, time shift, frequency shift, then time reversal. If x of n gives you x of omega, x of minus n gives you x of minus omega. Okay, this is also important. Time reversal property. Then there is a frequency differentiation property. If x of n gives you x of omega, then the moment you see an n getting multiplied in x of n, then it is time for differentiation in the frequency domain with the multiplication of a j. This is a little different from your Z transform thing, but similar but different. Okay, remember that property. Then what is there? Then the all important convolution property. This is also very important. Convolution property. What does it say? Convolution becomes multiplication. Here, convolution becomes multiplication. Okay, what about multiplication? Multiplication becomes convolution. Okay, convolution becomes multiplication, multiplication becomes convolution, except for this constant 1 by 2 pi. It's a dual, right? A duality property. Convolution becomes multiplication, multiplication becomes convolution, plus the along with the duality, it's a duality principle anyway. It's a duality principle. Okay. Then what else? What, which is other property? Yeah, there is something called as Parseval's theorem. There is something called as Parseval's theorem. This is also very important property. What is this expression, by the way? Now see, this is the essence of a Parseval's theorem. This is the essence of the Parseval's theorem. But here there is a small catch that here there is a small catch that if at all, okay, what does the theorem say? Multiplication with summation. Okay, multiplication with summation is equivalent to 1 by 2 pi and the multiplication. Okay, it's a statement, but there is a very important thing here, which is if at all I simply replace x2 of n as x1 of n only, then you can see this here is the expression for the energy. Remember from the first module, energy is running sum of the running squared sum, that was the energy. Now if at all you have a very 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 large sequence x of n with a single or two frequencies, what you can do, you need not perform the running sum of the running squared sum. Rather what you can do, simply find the x of omega, square it and integrate it over the period. You should still get the energy. That is the essence of the Parseval's theorem. Okay. Finding energy in time domain and finding energy in frequency domain, whichever you are comfortable, you can use. Okay. So which all are the properties, by the way, for us, they are that are important? Linearity, time shifting, frequency shifting, time reversal, frequency differentiation, convolution, and Parseval's theorem. Remaining all also important. Okay. But then for the timing, for solving most of the problems, these are the properties which we have to use. Let us see how. And by the way, all these properties, any one of the properties, especially this one, especially these properties, proofs will be asked in exam. Okay, the state and prove the convolution property, state and prove the time reversal property. You should know how to do the proof. Okay. So this I will give as assignment. Okay, you need not submit me, but you should know it. Okay. It will definitely appear in exam. Will appear in exam. Okay. Okay. Yes. Now, yeah. So this is that homework I was talking about. Okay. Please do it. Non-submittable, but once we come to the college, that time we should have it on your notes. Okay. Now again here we are. Something similar, right? We had seen a similar problem. Now we'll see once again. So what is this? 1 by 3 to the power n into u of n minus 2. So we will not change anything of n minus 2 with u, right? We will never change anything with respect to u actually. So that should be kept same only. So what we can do is here this thing we will take out. So that this is also n minus 2. This also is n minus 2. Okay. This n minus 2, this n minus 2. Then afterwards, so 1 by 3 to the power n into of n. What is the DTFT? 1 divided 1 minus alpha z to the power minus 1 z replaced by e to the power 2. This is a standard answer. Now what you have to do is, we will use the time shift property. A shift in the time domain results in a multiplication by an exponential, right? This was a constant, 1 by 3 to the power 2, right? 1 by 3 to the power minus 2, that's 9. That was a constant. Now this term is because of the property. Shift in the time domain resulted in multiplication by an exponential in the frequency domain. There you have the answer. Okay. So we earlier had this u of n minus 4, right? U of n minus 4, right? In the earlier question. Now here we have n plus 2. Same approach. You can solve it using the basic formula by changing the limits. This is also one more option. Okay. This can be done much more effortlessly. Okay. So what other questions we can have? Here is a question. Here is a question. What is this thing, by the way? Finding IDTFT. This is a question of finding inverse discrete time Fourier transform. So are you uncomfortable that I suddenly came for the inverse Fourier transform? Actually, we want to understand the clever use of properties. Okay, that's why we have come here. So here also the approach for finding an inverse DTFT, not necessarily by substitution in the formula. You see the approach here. This is the same approach which was used in that transform, the partial fraction expansion approach. So here is the question given. Whenever you see this kind of questions, partial fraction is the method to be used. So what did we do? Split the denominator, factorization, split the denominator. Then afterwards, go for partial fraction. Here you have to substitute for e to the power minus j omega. Okay, just as the way you do it in the your Laplace transform, where you substitute for s. Here you have to substitute for e to the power minus j. See, substitution of e to the power minus j omega as minus 2 will give you, this term will go to 0 and you will get a. Similarly, substitute to minus j omega equal to minus 3, plus 3, sorry. Okay, plus 3 will get you b. Okay. So those substitutions will give you these values. Now we can see, now this thing is 4 into 1 divided by 1 minus 1 plus 1 by 2, right? 4 is a constant. 4 is a constant, e to the power minus j omega. Okay. So now using the linearity property and the standard pair. Okay. So what we'll do? We'll use the standard pair. Alpha to the power n into u of n, we'll assume it to be 1 divided by alpha e to the power minus j omega. Here instead of alpha we have minus 1 by 2. So minus 1 by 2 the power n into u of n. Constant is the constant, right? What is the linearity property? A1 x1 of n plus a2 x of n given gives you a1 x1 of omega plus a2 x of omega. So constant will remain constant. 4 will come here, 1 will come here, and linearity, addition will still remain addition, and the standard pair, using the standard pair and the comparison, we could get the answer. Okay. So what is that? Partial fraction expansion method basically. But what did we use here? We used the ready result, and we also used the linearity property for our advantage, superposition theorem for our advantage. Okay. What else can we do? Yeah, here is one more question. Here is one more question. What is it? Cos omega. Okay, 2 cos omega. This also you can see, this is not your DTFT. Here you have been given the DTFT. You have to find the IDTFT. The moment you see a cos or a sine term, what you will do is you will simply replace them, represent them in terms of complex exponential. Split them in terms of e to the power j omega plus e to the power minus j divided by 2. Okay, that's what we did here. We got this thing. Now here we will use the property. Here we will use the property. So we studied that DTFT of delta n is 1, right? So I will consider this term as 1 into e to the power j to omega. Okay, 1 into e to the. So what is that property? What is that property? The property which you want to use here is this one here. Now see. This is the property. Multiplication by an exponential in the frequency domain results in shift in the time domain. Okay. So there e to the x of omega is equal to 1, right? 1 into. Okay. So what is it? Delta n. The DTFT of delta n is 1. So 1 multiplied by e to the power j omega, it should result in delta n minus n naught. Okay. We'll use that property here. Okay. We'll use that property here. So what happened here? So e to the power j omega delta n, e to the power delta n, it was 1. Okay, see, this was 1 here. So 1 into e to the power j 2 omega resulted in delta n plus 2. Okay, delta n plus 2. So which is this property, by the way? Did I tell you the wrong thing? Multiplication by an exponential, shift in the time domain. So did I tell you the wrong thing? Delta n was 1. Delta n plus 2 should be e to the power minus j omega, right? Okay. Yes, yes. The time shift property, sorry. So delta n, this is a minus, okay. So you can see here delta n minus 2 is, no, it is correct only. Delta n minus 2 is n minus 2. And this is time shift property, sorry. Okay, not the frequency shift property. Sorry, the time shift property to be used here. Okay, the time shift property to be used here. Okay, sorry, I made the mistake there. The time shift property to be used, e to the power minus j omega, right? The omega is not getting affected there. Okay, it is getting multiplied by an exponential. Omega is not getting shifted. Okay, I'm sorry there. Okay, so what happened? This answer turned out to be yes, delta n plus 2 to the power j omega delta n minus 2. So x of n equal to delta n plus 2 plus delta n minus 2. Okay, two impulses, one on the left side, one on the right side. Okay, only what this thing? So similarly, what about cos 2 omega plus j sin 2 omega? As I told you, the moment you see a cos or sin, simply replace them by complex exponential. Then afterwards go on substituting. Here, luckily what happened was, in this particular problem, what happened was e to the power j, e to the power minus j, that these terms got cancelled. These terms, you can see, these two terms got cancelled and these two terms got added up, and you are left with only e to the power j omega, 1 into e to the power j omega. So shift in the time domain resulted in this particular multiplication by exponential frequency domain. So what is the shift? Delta n plus 2. So that was that. Okay, so what other problems can we do? Similarly here we can see in this particular problem, as I said, what you have to do here, first thing first, what you have to do is get this u of n minus 2. We will get this particular term as a u of n minus 2. You can see here also we have introduced u of n minus 2, but we will not do that for cos. We will not do that for cos. For cos, what we'll do is we'll simply represent in terms of e to the power j omega and e to the power minus j omega. Okay. So first thing what we'll do is we will get half to the power into u of n is this. Half to the power n minus 2 into u of n minus 2 is multiplication by an exponential. Then afterwards a multiplication by a cos, right? Introduction of an exponential in the time domain, right? So if at all I have a to the power n plus 2, if at all I multiply by an exponential in the time domain, what will happen? See, now you have 1 by, see this here, e to the power minus j 2 omega, right? Minus j 2 omega. Now if at all I multiply this by e to the power j pi by 4n, multiplication by an exponential in the time domain results in a shift in the frequency. You can see omega is being shifted here. You can see the omegas are being shifted, hence you get an answer. Let me stop here today. We will continue tomorrow. Okay. Thanks for joining.